Hello everyone, welcome to the fifth lecture of mass transfer. This lecture is related to Fick's law of molecular diffusion. Now, what is Fick's law? This law states that molar flux is directly proportional to concentration gradient. Concentration gradient and cross-sectional area for molecules. Cross-sectional area for molecules, and inversely related to distance This is known as Fick's law. Now, molar flux. Now, first of all, we should know about the molar flux. What is molar flux? Flux is nothing but anything. Flux is the general definition of flux is something which are flowing per unit area. This is area per unit area into time. Now, molar flux is nothing but molar flux is number of moles per unit area, which is square meter into per second. It is mole per unit area into time. It is known as molar flux. So now, what is molar flux? Suppose this is a box, the control area. Suppose we have a box. This is the control. This is the control volume. Now there is some molecules on its one side. Suppose there is some molecules of component A. Suppose this is component A, which is on this side, and the concentration of component A on this side is very high, and suppose it is denoted by C1. Similarly, the concentration of component B, these molecules are transferring to this box from left side to right hand side, and its concentration here is very small, and it is denoted by, suppose it is denoted by C2, and the concentration here is denoted by C1. Now these molecules are traveling or cover some distance. Suppose the distance covered by molecule is delta Z. Suppose this is the distance covered by molecule, and delta Z is nothing but it is Z2 minus Z1. Final position minus initial position. Now due to the concentration gradient, here the concentration is very high, air concentration is very small. So due to these concentration gradient, they are transferring through a unit areas. This is the unit area, which is denoted by this. This is the unit area, which is denoted by, this is the cross sectional area, and the molecule are passing through this unit area. This is the area. So Fick's law states that the molar flux, which is moles of A, suppose moles, this is component A. So molar flux of component A is directly proportional to, molar flux of component A is denoted by JA. That is molar flux of component A. Suppose this is component A. So mathematically this law can be written as molar flux is directly proportional to concentration gradient, which is nothing but change in concentration into change in time, delta Z. This is the distance covered by molecule, and it is also say that flux is directly proportional to concentration gradient and inversely related to distance. As we know, is inversely related to distance. Similarly, flux is directly proportional to the cross-sectional area per molecule. Now, if we increase this cross-sectional area, then the flux will be increased. Similarly, if the concentration here is very large and the concentration here is very small, then the flux then the molar flux will be also very large. As the gradient because the gradient here is very will be very increased, and as the gradient increases, the molar flux will also increases. Similarly, when the area increases, the molar flux will also increases. Now combine these two relations. Suppose this is relation 1, this is relation 2. Now combine these two relations, we will get molar flux is directly proportional to cross-sectional area into concentration gradient. Concentration gradient is nothing but it is change in concentration per unit length. This is delta Z is length. So it can be for small area, for very small area. Suppose for very small area, this flux can be written as directly proportional to area into dCA into dZ. Delta C is nothing but C1 minus C2, and delta Z is Z2 minus Z1. As C1 is larger than C2 because concentration here is very large. Concentration here is very large. Suppose this is the concentration here is very large and here is very small. So this term is negative. So we will get finally we remove the proportionality constant. We will put DAB, which is constant, into area, cross-sectional area, into dCA by dZ. As dCA by dZ, as dCA by dZ is negative because C1 because sorry C2 minus this is C2 minus C1. As C2 is less than C1, so this term will be negative. And as we know that flux is positive quantity, so to become positive we will put here negative term because this term is negative, and negative multiplied by negative we will get positive flux. So this is all about Fick's law of molecular diffusion. Now this term is known as diffusivity. This term is nothing but it is diffusivity of molecule A and molecule B. Suppose this is the diffusivity. This is the extra. This is the DAB is diffusivity, and its unit is square meter per second. And it is nothing but suppose if there are, and its meaning is suppose if there is molecule A. Suppose this is molecule A, and these molecules are diffusing in, these are traveling in other molecules. Suppose this molecule suppose this is molecule B. Suppose this is the molecule of gas A and this is gas B, and gas A is traveling in gas B. Suppose these molecules are traveling in gas B. So the speed of molecule A and molecule B is known as diffusivity. How much air travel in the molecules of gas B? It is nothing but diffusivity of A and B. So these are all about Fick's law of molecular diffusion. Similarly, if someone is interested to find the units of, then the unit of DAB is meter square per second. Similarly, area is meter square, and the concentration is mole per meter cube into length. So these are cancel with this term, and we will get mole per second. So molar flow rate. Now if and this molar flow rate is denoted by JA. Now if JA is divided by A area, then we will get flux, and if we divide it by area, then it will become meter square. So this is the JA by area. So it is molar flux. It is nothing but molar flux. So thanks.